Hello, this is Mike of the Home Supercomputing Research Facility. I'd like to welcome you to a simple demonstration today of how to generate ARM64 assembly language code on a Mac OS Apple Silicon processor and also run the same code on Raspbian OS on a Raspberry Pi 5. And the goal and the purpose of today's demonstration is just to run simple debuggers to get into the registers and see how to debug these things. When I first dove into the Apple Silicon processors and debugging stuff, there was a world of stuff out there that didn't make any sense. I relied on a lot of tutorials by Perry Kilvilix, if I get this guy's name right. He was a chairman at a computer science department out in, I don't know, it was Wisconsin or Minnesota or somewhere, and he has since retired. But he left a wealth of information, but a lot of it was hard to stumble through, and there weren't any simple building blocks, what I felt like, to piece his components together. He left a wealth of information out there, as well as several other people on this stuff. I have several good books on programming the Raspberry Pi, and I also have an excellent book I've been using. Once you start understanding this stuff and getting your feet wet, I have a great book by, who's this here? This is by Maria Azaria Markstetter, ARM Assembly Eternals and Reverse Engineering. It's actually for going against malware, but the book is a gold mine on assembly language programming and learning registers. That's kind of how I back engineered a lot of this stuff once this stuff started making sense, getting play with it. But the biggest problem is I had to know how to get into a debugger specifically on Apple Silicon, which it didn't seem too friendly at first. And Apple didn't seem too happy about producing information on how to do assembly language programming on their Silica. But at the same time, since we're on ARM64, I also was doing a lot of my code development and learning on my Raspberry Pi 5, which is Raspbian OS. So you'll see how I go back and forth here on developing stuff, because initially the only debugger I had was on the Raspberry Pi, and that was GDB. And of course, on Mac OS, the only debugger you have is LLDB. So we're going to develop code that will run on both and access the debuggers and see what it looks like. If you look at the screen, I have a simple framework code. I call it debug_example.S to identify this as an assembly language source code file. For this demonstration today, if you're looking at the headers I have in the program, we're going to implement a simple for loop. In C, it would look like for I equals 0, I is less than equals 6, I plus plus. Next I do nothing. And we're going to compile this today using GCC on both Mac OS and the Raspberry Pi. So you see some of the header here I've filled out. We're going to fill in the code here, but I want to leave the header I have intact here. This came from Perry Kilovik's examples, where he set up his conditional macros to go in and determine if you're assembling this code on a Mac OS, use this global main. You'll see that's the only code we have right now. Else, if you're on the Raspbian or Linux version of ARM64, use this global main header, main semicolon, and if. You'll see that right there. And the other piece of our small code here is just a simple return. We're going to fill in the blanks. We're going to write our simple code to do a for loop. So I'll keep the coding simple here today. Let's dive in. What code do we need first? We need to set up our simple for loop. So we are going to use the 64-bit X register. I'm going to initialize that to 0. We're going to do a move, which is actually a copy. X20, comma, X0 register into that. And that's for our purposes, it's for I equals 0 is what we're setting up here in our for loop. Now we're going to set up a label to mimic the for loop. So we're going to do this here. We're going to do a for loop label. And we're going to loop back this. So what do we need next? We need if I is less than or equals 6, right? So we're going to do a compare X20 with the value 6. And that would be equivalent to if I is less than or equal to 6. What do we do? If it equals 6, we're done with this loop. Branch on equal. Actually, with compared as subtraction, if I remember the documentation right. So when it becomes 0, branch is equal to 0, we got to do a branch out of here. Get us out of here. We're done. We're done with the loop. So we're also going to need a done down here. And we'll start that. I'll file it here, or start the label. So done. So what else are we going to do? We're not quite done. So we got to do an I++, right? And this is the brute force way of doing it. We actually have better ways than ARM64, but for intents and purposes, we're going to increment like this. And that is our I++, our for loop. Now what are we doing here? We are not done, so we need to branch back to our for loop. There we go. And that, so to speak, is kind of like our next, right? And we're going to mangle some words here. So what do we do here? If we're done, we need to set up the program to go in and copy into, this is part of the return procedures for this, W0, which is the 32-bit component of the 64-bit X0. If we're looking at this right, we're only looking at 32-bit. We're going to pass in, copy in the W0 register. And then we're just going to return. Done. I'm going to save this. We're doing this all in Xcode. By the way, let me see if you have this come up here. I am using the ARM assembly language. You see this right there? ARM assembly language syntax support, and that's why I'm getting all the correct color codings for the labels and the commands. So let's do this. Let's do a save. See what we got. File. Save. Did we get it? Did we get it? In the directory here. Class minus L. There's my debug underscore example.s. We modified it 908 this morning. So we're going to now do a GCC. It comes with CLang, but I use GCC minus G to compile this. We're going to do our debug underscore example.s. Do we survive? Did we make it? No mistakes, Mike? All right, we got it. We got it. So what we want to do now is, it probably won't do anything. So we just want to execute it flat out. A.out. Hope we don't get any core segmentation dumps or anything. Nope, we did it, but it does nothing, right? Print nothing to the screen, did nothing. So how do we know what the code did? We're going to dive into, I have a couple instruction sets up here, right? You see this right here, put into the source code. We're going to run LLDB on A.out. That's the file that was generated. We can actually link and create a file to do this, but this is just a simple brute force way, because when you're developing code, you're going to have to spend a lot of time inside the debugger, or LLDB on Apple Silicon. Let's do this, LLDB. Let me type here. And initially want to go in and set a breakpoint. Break. Set. And it's minus main, remember, for the main header file, to go into the main program that we set up previously. Name minus main. There we go. That looks better. No, it doesn't. Mike can't type. There we go. Okay, breakpoint set. We see that there? We're good. We're good in the hood. Let's do a run. Okay, we're seeing registers there. Good. Let's do another breakpoint. breakpoint set minus name. We want to look into the for loop now. For loop. Let's continue. What do we got? Now we're down in our code. Does that familiar? Compare register, the 64-bit register X20 with the value 6. Let's take a look. What do we got in registers? Register read X20. Yep, it's set to 0. Is that what we were going to do? We see up here, remember, we initially in this thing, we moved the 0 register to X20. That looked good so far? So we're starting our first loop. We're dropping in, comparing it X20 to 6. Is it 0? Is it 6? No, we see our register 0, right? We could also do this too, just for laughs. We can do our, see how it looks, it's 64-bit right now. We can look at the 32-bit version by doing register read X20, and I think it's space W20. So let's look at the simultaneously to see what this stuff looks like as we go through this. Here we go. And let's continue. Let's get our next value. What's happening now? It's register read. Let's look at both of these. What's in the registers now? We're at 1. We're incrementing, right? We're down here at add X20. We passed that. We looped back up. So is this program behaving as we expected to? That's why we did a simple loop. Let's continue. Let's do one more iteration of the loop. C for continue. It's in our registers. Oh, look at, they're incremented 2. I want you to see too, see how X20 and W20 are the same. So when you work with values in X20, we could see the 32-bit value in the W20 register. That's kind of a neat little thing we can see here too. So let's continue. We're going through our loop. We expect 3, right? Our next iteration, we're adding. So W20 should have the value of 3. Register read, we have 3. Oh, the applause is deafening. Here we go. Here we go, guys. Let's continue. Let's go grab a next value. Should be 4. Should be 4. Bam. So we're looping. See, that's why we're set the breakpoint for loop, because it's branching back up to for loop every time until we get the value 6. So continue in a loop. What do you expect, guys? What do you expect to see here? 5. There we go. Continue. So let's do another iteration. What are we getting? So we should be seeing 6 in these registers, right? There's 6. Now what do we expect to happen? What happens when we hit this compare right here? What happens when we hit that compare value? Because now we added this, we're at 6, now we're looping back up. What do we expect to see? Let's find out. It terminated, right? What's our registers? Can we read the registers here still? Nope, we're done. We're done. So what happened? Did we do our code properly? So if it equals 6, compare equals 6, branch to done. What did done do? It moved copied a W0 register into W0, which we need to exit the program and return, and we're out, right? It kicked us out. Good stuff. Now let's copy this program over to the Raspberry Pi 5 and see if we get the same results. However, we're not going to be using LLDB over there. We're going to be using GDB. And I have Visual Studio Code also on my Raspberry Pi 5 over there. And we'll look at Visual Studio Code over there, but I'm also going to use CodeBlocks. Unfortunately, CodeBlocks doesn't work on Apple Silicon. There's a version built for it, but it crashes and it doesn't work. I wish that would have gotten fixed, because we can use GDB natively here. And I don't know if we can use GDB natively here in Apple Silicon. But we're going to use the GDB debugger natively over on my Raspberry Pi 5. And let's hop over to that one. Okay, so here we are now on my Raspberry Pi 5 workstation. And I'm using Visual Studio Code on the Raspberry Pi 5. for this initial demonstration. LLDB, I don't know if it's on the Raspberry Pi 5, but I know their default debugger is GDB. So again, here we have the same code. I just VNC'd into my Raspberry Pi 5 from my Mac Studio, and it's the same code. So here we go. We'll see it here. It looks familiar, right? Let's kind of scroll up and down. It looks familiar. No tricks here. Here's our macros for conditional assembly, where if it's Apple, then uses global_main that Apple requires. Else, we're on a Raspbian OS system or Linux and just use a global main with no underscore. Here's our label for the for loop, and here's our basic for loop as we did last time. And we have our terminal right underneath here. Again, I am using on this, what's my extension I have on this guy? Still using the ARM. Let me see if I can pull this up here. Dave's ARM or ARM assembly. Here it is right here. Dan C. Underwood. For the syntax, that's how I'm getting this. I'm using the same one. It's kind of nice on Visual Studio Code, so I can have my same environment on both my Mac OS, Mac Studio, my my AirBook, my old Mac Mini M1, so and so forth. So it's kind of cool. I can hop around different devices and just I'm trying to compile or doing an experiment now where I could write either a game or something that will assemble on both a Raspberry Pi 5 and the Mac OS, and just use conditional assemblies and stuff to figure out which the final target build is going to. So that's kind of what we're doing here. This is what we're building up for, guys. We're keeping it simple, stupid, because I when I went through this, I had a hard time just getting the debugger working. It wasn't easy. It wasn't intuitively obvious to the casual observer. That's something my physics teacher used to say to me when we looked at quantum physics, and it's like, what are you talking about? And he would joke and turn around from the chalkboard and go, oh, it's intuitively obvious to the casual observer, right? Which means nobody knows what the hell is going on in quantum physics. Same here sometimes. What is going on? So I wanted to keep it simple, and I wanted you to do building blocks to go back, like I said, and go through the book I mentioned. ARM Assembly, Eternals, and Reverse Engineering by Maria Markstetter. I think you should go through this just to learn what it does. Another good book is Programming with 64-Bit ARM Assembly Language. Those are my two books I'm using here. I have them unfortunately, the Maria Markstetter's book, I don't think it's available on Kindle, because I like having those on Kindle too. I can go back and you can sit in front of the TV and just troubleshoot off your Kindle or your iPad. Let's dive into this here. We have the conditional macros, and since we're on Raspbian OS 64-bit, this is a Raspberry Pi 5. I think the same will work here with the Raspberry Pi 4B. I think it's also 64-bit. So this should work on that also. I don't have my other one fired up at the moment because I'm using it for some other research purposes here at the Supercomputing Center, so to speak. So yeah, let's look at this. Raspberry Pi 5 now. Same code. So what should happen here? We should be able just to hit file save. And let's do an ls -l. Do we have anything here? Okay, so let's do our GCC -g, because we want to assemble for our debugger, our GDB debugger. And we have debug _example dot capital S. You can use lowercase s, but I like to use a capital S. I think old school, when I was doing this on the Sun microsystems and stuff, it was capital S. And so for assembly, I still stick capital S. Both uppercase or lowercase will work, but I'm old school and keeping tradition. Here we go. Let the old man have his day. Boom. We made it. Good. Did we get anything? ls -l. Do we have an a.out? We sure do. Let's run this thing. It's going to do nothing like before, but we don't want any segmentation faults or any errors we have to look for initially. Bam. It ran. Gosh, Mike, what do we do now? Let's load this sucker in GDB. I am not a GDB expert. I had to come to speed on GDB with this one. Actually, it was a long time ago when I was working my old stint at Cisco Systems, software engineer. Used GDB quite a bit, and then it's been some time, guys, so to speak. GDB a.out. Again, I'll use the linker and stuff later. We'll build the programs, program names, but I want to keep this simple for you guys, just to get into the debugger and start playing with it. Whether you're on the Raspberry Pi 5, the 4B, or on Mac OS, I gave you two venues now to play with. So I have my primary platform of choice has been the Mac OSs, which got me in this endeavor. I just love assembly language. I've been programming since the TRS-80s, the Apples. I got a Commodore 64 back here in the Home Supercomputing Museum that I still do assembly language on. But I do it more virtual now than using that old machine. It's kind of like a relic now, and I'm afraid it'll break. Probably not. It was built in the 80s. Probably won't break. Anyway, I just love messing around with assembly language. I have it down to, I did with Cray computers back in the 80s when I was getting my computational physics degree. The PDP-11s, the VAX, all sorts of crazy computers I worked with on assembly language. The Macintosh, that had a beautiful assembly language. The Motorola, it looked very similar to the digital environment of the PDP-11, which I thought was kind of cool. It was almost similar in look, except one was octal, one was hexadecimal, but I digress. Let's load this bad boy up in GDB. GDB A dot out. What we got, Mike? Okay. Can we do a list? What do we got? There's our code. Hey, look at that. It's inside. We got that. Looks like our code, right? Let's do this now. Let's set a breakpoint. Where are we setting the breakpoint to? Can you guess? Are we setting it to the Apple _ main breakpoint like we did before? Or because we're in Linux, we're setting it to this main breakpoint? I'll take Linux for $50, please. Main breakpoint, Mike. That is correct. Here we go. So breakpoint. Let's do the main. What we got? We got a breakpoint main. Awesome. Let's do a run. Does this look familiar? Should look like the LLDB. Some ports up. There we go. Breakpoint main. What do we got to do now? We got to set a breakpoint for the for loop. That's where we want to spend our time. Keeping it simple. Bam. We do a container break loop. What do we got? Yep, there we are. So what do we do now? Instead of read reg, we got to do an info reg. And now it looks like the same syntax. Let's do the, like we did before, the X20 and the W20. So we're looking at the 64-bit register, X20, but we can look at the lower 32-bit contents of it if we treat it just as the 32-bit register W20. Bam. Oh, it didn't like the comma. That's right. Boom. There we go. There it is. There it is. We are dropping in. Look at the values. They're 0. We're on our first iteration. Oh my gosh. The applause is deafening. Here we go. Let's look at the registers again. We should have 1s in there. Bam. It's doing its thing. It's doing its thing, right? We just had the I++ right there. We're not at 6 yet. So let's continue. Let's continue our loop. Compare it to X20 to 6. We got a 6 in there. No, what's the values? The registers, they should be 2s, right? Oh, applause is deafening once more. Hey, we're getting there. Oh my God, it's exciting. When something works, it's exciting, even at low level, because you got to have tools now. I'm teaching the basics just to look at the registers to see what the heck happened. My next tutorial after this, I'm planning on doing an integer array. So we're going to break up the complexity a little bit and slowly get you guys built up to look at this stuff and debugging and what's in arrays, things like that. But right now, we're just looking at how a for loop works. Because guess what? We're going to build an integer array of 6 elements. Oh my gosh, we have a for loop for 6 elements. Yes, sirree. Well, I'm yapping my lip and I'm not paying attention. This should be 3, right? There we go. Continue. We incremented. It should be 4. Continue. One more iteration of the loop. What do we got here? It should be 5, right? 5. Cool. Continue. And where are we at now? We have 6. What happens now? We should break out of the loop. We should break, guys. Boom. Exit normally. We got it. It did it. Let's quit out of this now. There is something cool on the Raspbian OS that is not available. I mentioned earlier, I tried to get CodeBlocks to work on my Apple Silica, and unfortunately, nobody's supporting it. There's a older piece of code that will install and it does nothing. It just fires up and goes wah, wah, wah. However, CodeBlocks does work on the Raspbian. Let's take a look at this here. Why is this important? Because as a built-in window debugger right into the environment, it's GDB. So you can do it this way. This is a matter of preferences. I can do it this way, or sometimes I just like going from the GUI environment. So what I do is go to my programming here, CodeBlocks. I think it's app install code, something like that. Or no, I think it was app install code was Visual Studio Code. Look it up. Look up which one installs CodeBlocks and get this. It's not there by default. Launch CodeBlocks. I'm going to show you how to set this up. And we want project, okay, a new one, file. New project. And the type of this project is going to be a console application. You see that? We're doing a console application. Click console. C++ is fine. We're going to get rid of it, but we need the basic project components from that. So hit next. Project title is debug example. CodeBlocks. Let's use that. And where's it going to go? Go here. Next. I want this. Leave this. Hit just, yeah. So we go. So we have our basic debug example. Okay. And we have a C++ source. We don't want that right now, but however, let's do this. Let's go back and open the file. This one right here, this is the one we imported. We're just playing with in Visual Studio Code just a minute ago. Open that. And we're going to do a project, add files. What's this one here? And open. Okay, just okay. There it is. See, now we have an ASM source, assembly language. It's right there. And that's this guy. That's the one we're using in Visual Studio Code earlier. The royal we do not want this. Let's get rid of it. Remove file from project. Be gone with you. We have this guy. So what we got now? We got our source code. Look at that. In this nice, beautiful GUI environment. There should be a way to, color code all these different labels, mnemonics and stuff in assembly language. I haven't really got to that yet. I'll have to figure it out. But now that I got Visual Studio Code 2, and I'll probably be going back playing makefiles or play with this. But if you want to be quick and dirty about something and test stuff out, it's the way to go. So let's do a build. Let's do a build and run. What the heck? Let's go for broke. It ran. It built and it ran. Let's do this now. Let's open. Over here, you see this? It says debugging window. Open that. CPU registers. Oh, yes, please. Okay, that's what we got. Now, what we're going to do, see this right here, step into. Got this. Let's do a step into. Look at that. Look at that. Come back here. We got our CPU registers. I'm using this right here, step into. So we are about to set X20 to 0. See that? We're right here. That's where in the code. I'm going to go back to step into. See that? See what happened right there? This is cool because you can look at your code and step into your code. So now X20, as we predicted, should be 0. We'll do our comparison. Nope. Is that? Nope. So it should branch back the loop now. Boom. And we incremented X20 to 1 as we did down there, right? It's working. It's looking good, guys. Compare. Is it 6? Nope. we're not branch to equal. So therefore, we're going to increment x20. Should be 2 now. Bam. And we're going to loop back. Is the value in x20, which is 2, equal to 6? Nope. So we're not done. Now we're going to increment x20, I++, and we're at 3. This is cool or what? I love this part. This is nice. This is very nice. And so we branch back to loop. Let's do this. Okay, let's keep going. See what we can do here? We can view all the registers at once. If we had a bigger issue we're dealing with, we'll look at memory locations like pointers to our integer array, which we're going to look at next time. And we can look at our loop. Did the loop blow up, or are we still doing good? So we're still stepping. Nope, not 6. We're going to add 1. We're 6 now. What happens to the loop? Branch back to loop. Do our comparison at this line number 30 right here. Compare x20 to 6. Are we at 6? We should be. What's going to happen? Branch and equal to done. Look at that. Look what it's doing. Look at W0. So it'll also modify our X0 up top. X0 is a 64-bit version of the W0 register. So that could go to 0 when we hit next step. Boom. So you go to 0 up there. And we're returning. We are done. We are done. Let's kill this. Yes. That's it. It's pretty fancy, huh? So I wanted you guys to see that too, because I think I would love to have CodeBlocks on Apple Silica. I wish I knew enough assembly language coding or C coding at that level on the new Silica to finish this. This would be a nice to have, really nice to have. But I want you guys to see it. I hope you guys enjoyed this from Mike's home supercomputing facility here and research center, where we're going to start doing some more ARM64 coding just for fun and play around stuff. I want to implement some algorithms too. Way back when. I am a retired programmer. I also have my quantum computing certification from University of Chicago, which I got back in 2022. So if we want to talk about weird stuff, or maybe do like some weird algorithms in assembly with quantum computer or something, we're going to play with some stuff, but I want to get you guys up to speed, and I want to just keep this so it's not overwhelming you, that you can sit down, less than 40 minutes we did here and learn stuff. So if you like this video, you like the content, smash the like button, and also subscribe to this for Mike's Home Supercomputing Research Center, where we're going to look and dive into some more tutorials and break down stuff where I don't want to be an academic egghead. I just want to get you hobbyists up to speed. Years ago, when we did this, decades ago, it used to be fun to stay up in the middle of the night and play around with assembly language coding. I want to get back in that same thrill, but somehow all these different forms of Windows operating systems and AI and garbage that's been lapped on top of it, it's taken the fun away from us. So we're going to fight and get the fun back, man. This is hobbyist coding, and we're going to build some cool projects or whatever. Yep. So thank you. And remember, kids, never ever read the manual until you're at least 7 hours into being stuck in the programming problem. Until next time.